Hello everyone, my name is Sam Kolodrovitz, and today I'm going to walk you through my final project, which is an analysis of fear and other emotions being used within American news media. For anyone somewhat familiar with American news, there's one phrase that describes how stories are told and what makes the most popular story. If it bleeds, it leads. Essentially, this phrase tells us that if a story can scare the audience and make them come back for more information, the more likely it is that that story will be published and be more popular. So why is this topic important? The news and an individual having a strong media literacy is vital. It allows them to stay up to date with current news events and see how it affects their everyday lives. It is even more important, however, to understand the motivations behind news outlets and the tactics they use to keep viewers coming back to read or watch more. With that being said, there are two main questions I sought to answer this semester. First, is it possible to quantify the level of fear among other emotions in news articles across various outlets? Second, is there a difference in the level of these emotions being used between different outlets? To answer this, I did a two-part analysis. First, I attempted to train and test an emotion classification model using PyTorch, trained on an initial dataset with over 400,000 tweets, with corresponding labels to an emotion. These emotions include fear, anger, sadness, joy, love, and surprise. Second, once the model is trained to a sufficient level of accuracy, I wanted to use this model to predict the emotion real-world articles portray. The data will first be obtained through a web scrape of two sites on opposite ends of the American political spectrum, and now, once it is attained, I can load the best model that I have chosen in part one and test and predict the emotions being represented within these articles. Here we can see an overview of the project's pipeline and how I achieved my results. A large portion of my time was spent in number 1 and 3, which is the data cleaning and pre-processing step and the actual creation of my machine learning model, training, testing, and tuning it. Additionally, as I mentioned, for part 2, I will be scraping news articles from two websites, CNN and Fox News. Then, once these articles are obtained and gone through the same data pre-processing steps done in part 1, I will use the model created in step 3 to predict this output. In this slide, we can see the steps required to process this incoming raw text data and make it ready to be used by PyTorch. We start with a standard sentence, as seen on the left. Next, each input text sample needs to be tokenized, which is the process of breaking this raw text data into smaller tokens, or in this case, individual words. Next is to remove the words that contain little to no inherent value, such as the, I, and similar words. These are called stop words, and their inclusion in the model would not add much, but only increase the complexity of the model. The last step is a process called lemmatization, which is the word for the process of removing the inflectional endings to words to only include the base form of a word of the lemma. As you see here, feeling becomes feel, days become day. So this has to be done for every single word in every single tweet within the dataset. Several more steps are needed before PyTorch can work with this incoming data and use it to train and test a recurrent neural network. First is the creation of a dictionary that contains all emotions and tweets with corresponding emotions. This is what is inputted into the PyTorch dataset object to be used for training the model. We then need to create a vocabulary which contains all words within a dataset with a corresponding index. The vocabulary is then used to transform each token into a vector of integers, or a tensor of integers, which we'll see on the next slide. On the bottom left, you can see the final format of what is inputted into a PyTorch dataset model. After the dictionary was created, each tweet is represented as a tensor of integers, where each integer is the index of the associated word within the vocabulary. This group of tensors is then transformed into a PyTorch dataset object, which you can see on the right, which allows the PyTorch to handle the data, easier indexing, and other necessary steps. When training and testing my model, the first thing I wanted to optimize was the problem with my dataset's imbalance classes. As we see, the original dataset on the left contains a much larger number of tweets labeled sad and joy. This could become a problem within testing, as this could lead to sadness and joy being predicted at a much higher level than, say, surprise, which has only around 14,000 samples for that emotion. For this reason, I chose to use 3 different data sets and tested the impact of each data set on the accuracy and total training time. These include the original data set with over 415,000 samples, you see on the left, a data set where sadness and joy are randomly downsampled to only 50,000 samples in the middle, and a completely even data set where each emotion has only 15,000 samples. Here's another look at the 3 data sets being trained and tested with the breakdown of the sample size for each emotion. Again, you can see that sadness and joy are much more highly represented in the full data set. The next problem I wanted to address is the high prevalence in the data sets of words that don't provide much meaning on their own. As you see on the screen, which is a look at the top 100 words within the entire data set. There are many words like feel, go, get that are prevalent for each and every emotion in the entire data set. I wanted to test how a model would differ, and if I were to leave out these additional stop words in addition to the standard stop word dictionary. The last parameter I wanted to tune was how changing the batch size would impact the accuracy of the model. Below, we can see the first set of models, all 3 standard RNNs trained on 3 different size data sets with a batch size of 1. As we can see, the test accuracy for each data set is relatively high, but the training time, which is the graph on the right, is substantially higher for the larger data sets, with the fastest model taking over 25 minutes. As we move on to a higher batch size of 16, we see that the training time has drastically decreased. The smallest dataset with 15,000 samples each was the worst performing model with this batch size, but took much less time. This is important because a shorter runtime allowed me to train my final model for many more epochs to achieve a higher accuracy. Lastly is training the models with a batch size of 32, which ended up being my choice for the final model. Unlike previous iterations, the model trained on the 15,000 sample dataset performed at a high accuracy from the very beginning and took a much shorter amount of time. Here we can see these results represented in table format. As mentioned, the full dataset had a very high accuracy for both batch size 1 and 16, but we see the drastic increase in training time. So for my final model, I chose to go with the 15,000 sample dataset because I believe that the trade-off between training time and the extra information the model would get for a full dataset is negligible. As I mentioned, I wanted to test whether including additional stop words within my dataset to be deleted from each tensor would have an impact on the model. And as you can see here, when I left out a list of 10 additional words in addition to the standard stop words, the model accuracy actually decreased. For that reason, in my final model, I chose not to include these additional stop words and keep the standard list. With that being said, here's the recurrent neural network that I chose to use as my final product. It uses the dataset with 15,000 samples per emotion, as the benefit for the shorter epoch training time greatly outweighs the additional samples, uses a batch size of 32, has a single hidden layer with 256 hidden nodes, and was trained for 25 epochs. After training, the test accuracy for this final best model was around 82.5%. This actually greatly exceeded my expectations. In a similar paper using a similar data set, the highest overall test accuracy was standardly less than 70%. Now that I've shown you the model used to test real-world news articles, I can get into the final results of my analysis. Here's a brief overview of the articles that were scraped from both CNN and Fox News. In total, I scraped 50 articles from each site, and the average word length for each site's articles can be seen on the screen. It is important to note that since my model was trained on tweets rather than news articles, the word count from each input sample in my training dataset is much smaller than what you see on the screen. I chose this data set because it was already labeled. It is something to consider when seeing the results. First, we can take a look at the distribution of emotions from just the articles obtained by Fox News. As we can see, fear and surprise are the most popularly predicted emotions within the articles, with anger and sadness following close behind. It's also notable that aside from surprise, articles classified as positive, including joy and love, were relatively small within this data set. Next, looking at the results from CNN, we have a very similar story. Fear and surprise lead the pack in the number of articles classified as either emotion, with anger and sadness closely following behind. Again, joy and love, the two most positive emotions, were the least popular. Lastly, when looking at the results from the entire list of scraped articles, we see that a pattern has emerged. Articles that are much more likely to be classified as a negative emotion or surprised, much more than these other positive emotions. It's also important to note that with hundreds of articles being written every single day on each news site, the emotions and emotional language being used is likely to vary. However, even with such a small sample size, it's really interesting to see that a similar pattern emerges across each news site. Lastly, to drive the point home again, when looking at a histogram of the polarity value assigned to each article, while the majority of the articles hover around 0, or having a neutral sentiment, there's an obvious skew towards -1, or being much more negative. This corresponds with a histogram that would be associated with more negative emotions. To conclude, we'll look at the research questions and see if we can make any assumptions. First, from our sample, there's a clear bias towards several emotions, with the most articles being predicted as fearful, surprised, angry, or sad. The positive emotions of love and joy are the least represented emotions within this sample. Second, for our sample, it is not possible to determine the difference in the emotions being used between CNN and Fox News. Each site had a very similar distribution, with negative emotions being much more representative. It is possible that a different pattern could emerge for a different sample on a different day, but for what I chose, there was no real pattern differentiating the two articles, the two news sites. This brings me lastly to a few points on some future work I'd like to put into this project. First, as I mentioned, this sample was from a single topic. I chose opinion articles. It'd be interesting to see the differences not only between different sites, but also reporting from various news topics such as world news or sports. Second, adding articles from different dates would again be interesting to see if the same distribution holds or if it varies at different times. Here's a list of some sources that I used. I thank you for your time. And yeah.